Tree diagrams are a really handy way that you can list all of the outcomes of a multi-stage experiment and then find the probabilities associated with each one. So a bunch of tips here on how to do it. Not a bad idea to write these down. Some of them you might want to leave out if you already know. And I've got an example over on the side here, and we'll have a look at a couple of other examples as well. So first thing, use each set of branches to list the possible outcomes. Well, over here in my example it says toss 2 dice, find the probability of 2 6s and, whoops, that should say the probability of 1 6. Now the question's all about whether or not I got a 6. So when I toss a die, I know that there's 5 other outcomes, 1, 2, 3, 4, and 5, and then there's the 6 as well. With your tree diagram, think about what you're actually interested in by looking at the question. Here I've decided to make my outcomes 6 or not a 6, because it seems like that's all I really care about in this question. And that saves me from having to draw up all 6 outcomes of the die, 5 of which are kind of the same. They're kind of not a 6. So I've chosen the letters S for 6 and N for not 6. You can choose whatever letters you like as long as it makes sense to you. Now, second thing, write the probability of each outcome on the branch leading to it. So when I toss the first die, I can either get a 6 or not a 6. And my chance of a 6 is 1 out of 6. And my chance of not getting a 6 is going to be 5 sixths. Notice that these two things need to add up to 1. And if you've done more than 2 branches, you can have as many branches as you need. All of the outcomes should add up to a certainty, 1. Then I've got secondary branches coming off each of those to show the second toss of the die, or the toss of the second die. And I've written the probabilities on these branches, 1 6th, 5 sixths, 1 6th, and 5 sixths. Again, notice that each set of branches has probabilities that add up to 1, but that whole list would add up to 2, wouldn't it? So you've got to make sure you understand what it is that adds up to 1. It's each time something happens, it's certain it's something or something else. List the possible outcome combinations. So we do that at the end, and I've listed them in green here. I can either get 2 6s, a 6 and not a 6, not a 6 and then a 6, or 2 not 6s. Now the product rule tells us that if we want to find the probability of A and then B, where A and B are successive stages of a multi-stage experiment, we just multiply the probability of A by the probability of B. Okay, now how do we use that? Well, if I'm looking at the probability of getting 2 6s, I say, well, I'll need the probability of getting the first 6, that's 1 out of 6, multiplied by another 6th. Now 1 6th times 1 6th is 1 36th. And I can write the probability of getting to the end of that branch by just following the branches that led to it and multiplying the probabilities along the way. And that makes sense. There's 36 things that can happen because the first die lands and it can be 1, 2, 3, 4, 5, or 6. And then each of those 6 options has another 6 options for the second die. So there's only 1 out of 36 outcomes that is 2 6s. So that makes a lot of sense. I could go ahead and find the rest of the probabilities here. 1 6th times 5 sixths is going to be 5 36ths. And this one will be the exact same. And the probability of getting no 6s at all would be 5 sixths times 5 sixths, and that's 25 36ths. Now, in this example, none of those probabilities can be simplified as fractions, but I have a habit of not simplifying them even when they can be simplified. The beauty of leaving them unsimplified at this level here is that if all the denominators are the same, it makes it nice and easy to check at the end that they add up to 1. Because if I'm adding 36ths, I can clearly see that 25 36ths plus another 5 of them, another 5 of them, and another 1 of them, that's going to make 36 36ths. And these should all add up to a certainty, or 1. So now I've got all my probabilities there. I can answer any question I like. The probability of 2 6s is going to be 1 36th. The probability of getting 1 6 though, well, this is a little bit more complicated because there's 2 ways that it can happen. So I'm going to zip down here to, if you're interested in more than one outcome, or sorry, more than one combination of outcomes, you must find the probability of each and then add them. Now, why do we need to add them? Well, if we're interested in finding the probability of getting 1 6, and it's not specified whether it's the first die that's going to be a 6 or the second one, and we don't mind, then we need to say we've got twice the probability of it happening, because it could happen by getting the 6 first, and there's 5 chances out of 36 of that happening, or it could happen when we have the 6 on the second die. Now, as soon as I said that word or, that's a really good hint that we need to add. So 5 36ths plus 5 36ths is 10 36ths. And I can then simplify that and say it's 5 18ths. Now, if you are using at least, or if you're coming across at least questions, consider using complementary events. So if I had a question here that said, what's the probability of at least 1 6, there's 2 ways I can work it out. I can either say, hey, that's 2 6s, or 1 6, or this other version of 1 6. I could add those together. Now when I do that, clearly I get 11 36ths. But there's another way I could do it. I could say, what's the opposite of getting at least 1 6? No 6s at all. Well, 1 minus no 6s at all is also going to give me the chance of getting at least 1 6. So in this case, it was nice and easy. I had all my probabilities there and I could add them together. But if you had a really big tree diagram with lots and lots of branches, and it would probably be a lot easier just to find the probability of that one branch that you don't want and subtract it from 1. Now, the only tip that we haven't mentioned here is this one. It's helpful to imagine one event happening before the other, even if they occur simultaneously or at the exact same time. Now, if the events are independent, then the order isn't going to matter. That's because we're multiplying a probability by another probability, and it won't matter which way we do it. Now, this only works and is okay if the events are independent. In other words, the outcome of one thing isn't affecting the other. So if I toss 2 dice, if one lands on a 6, that doesn't affect the other one's ability to land on a 6. So they're definitely independent events. So it doesn't matter which dice is listed first. And in fact, if they land at the exact same time, it's still fine to say, well, I looked at this one first, so we can imagine it happening beforehand. Because that makes it easy for us to draw out our tree diagram in a way that makes sense.